So, what I want to talk about today is a little bit about population growth. So I talked about how we need to determine water demand. We need to know how much water we need, how much water is available. And one of the ways we can do that is by studying the population of your municipality, your city, your region. Whenever I want to talk about very broad terms, I think I'll use the term region. But a region can be anything that you define it to be. So a region can be the school. Let's say you're designing a water system for the school, the region can be the school. Or it can be the city of Marietta, or it can be Coffee County. So really the region is a very broad term that just, I just use it to talk about whatever it is you're studying or designing for. All right, so we mentioned last time that if you're going to design a water system, you don't really design it for the actual population at this very moment, right? We need to consider things like population growth and population movement as well. Okay? Now, of course, we can't really estimate the population growth perfectly, like very, in a very perfect way. Instead, we're going to have to estimate it through some assumptions. Okay? That's pretty much what we're going to do. Instead of going through some nice analytical methods, we're going to have to go through empirical methods that use a lot of assumptions. This is where statistics kind of comes into play. We already covered, I think, linear regression. If you took data collection class, at the end we covered linear regression. I think linear regression is going to be a good method that we can use with its own limitations, but at least it helps us get a starting point. So here's the thing. The reliability of any population growth model, or any model in general, right, depends on the validity of the assumptions that you make for that growth model. A lot of methods, I would say most methods, are going to assume that future changes in population follow the same pattern as past changes. So if you had this amount of population and your population increased by 100% in this many years, then a lot of models say, well, in the same amount of years, it's also going to increase by 100%. Is that completely correct? Not always. There's always some nuance and variation, but at least it gives us a starting point to start to estimate population increases. I would like to study, in this class if we have time, I would like to study two different types of methods for population growth. One for short-term population growth, so between 1 and 10 years, one for long-term population growth between 10 and 50 years. We normally don't want to design for larger population, larger times than 50 years, because typically water supply systems, we give them a shelf life of a maximum 50 years, definitely less than that, but at the maximum 50 years. So you typically don't want to design a water supply system and assume that it's going to last 100, 200 years. Yes, the Romans did it, and yes, it did last that long, but our designs are not going to last that long, especially with the rate of growth that we have now, which is incredibly exponential compared to what it was 2,000 years ago. So let's start with a simple method, I would say, for short-term population growth. A very simple method is the regression method. Now, I'm not really sure if statistics is a prerequisite for this class. Has everybody taken data collection and analysis?
Taking it right now.
Taking it right now? Okay. Well, in that case, let's introduce linear regression just a little bit, but I'm going to introduce it in a very conceptual way. I'm not going to go through the equations. I'm not going to go through this because I'm not going to make you go through all these equations. Just conceptually speaking, if you have a graph of data and that data seems to follow a linear trend, then what you can do is create a model that essentially travels or passes through the shortest distance between your model and the points, the observed points, for all the points. And this is what we call a linear regression equation. Essentially linear regression because it's a line, but not all regression has to be linear. You can do log power regression, you can do polynomial regression, but linear regression is the simplest one. Now, quick question, do you think population growth is linear from what you've heard or seen? No, right, good. So the only way population growth could be linear is that for every, one person, there was one birth, and that births and deaths kind of like coincided around the same time. So that's the only way, but that's not really what happens. Population growth isn't really linear. Now, does that mean that we can't use linear regression? I don't think it means that we can't use linear regression. I think what it means is that we need to be a little bit creative in how we use linear regression. So unfortunately, I didn't really prepare anything in Excel. I guess I should have done, but I didn't prepare anything in Excel. But if you ever have a graph that seems to follow a nice power relationship, so it can be something like this. or the other way, so a square root or an exponent, but any power relationship, one technique you can do is take this data, and instead of plotting that data, you can plot the logarithm of that data, the natural logarithm of that data. So what happens when you have power relationships and you plot them in log space, so you plot the natural logarithm of those data, essentially your graph is going to start to look a little bit more linear. And if your graph looks linear after you plot it in log space, so after you plot the natural logarithm of it, let's call this x, y, and this is the natural logarithm of x and the natural logarithm of y. If you do this, then you can fit in a linear regression equation. That line is still a linear equation, except that the variables now, instead of being x and y, such as this line, they're going to be log of x and log of y. But then you can solve for y, right? Because now all you have to do is raise it to the power, take the exponent to the power, and then you have your y value. So it's a pretty simple method to use linear regression without necessarily applying it to a data that follows a linear trend. That's one of the methods we can use. I would like to talk more about it, but I don't want this to turn into a workshop. And the theory is quite simple, right? The theory is just saying, well, plot it in log space and then fit a line through it. However, when it comes to the workshops, we will find that one of these days we're going to get some data. And I'm not going to say anything. I'll just say, well, we need to find an equation to fit this data. And hopefully by that time, you'll remember, log. So let's just plot the logarithm, fit a line, and that's our equation, a very simple equation. This is what we call the regression method. It's a very simple method. I mean, it can be visual. All I've done right now is visual. I haven't really used any numbers, but there's also some mathematical theory behind it. And in reality, both visual and math methods should work pretty well if your data set is quite large. If your data set is small, then consider using equations. But if your data set is large, just doing it visually, as long as you have a nice scaled paper, you should get a pretty decent regression model. There are a couple of limitations of regression. And the first thing is that regression models, they're valid for determining values within the range of observations. So if I come up with this linear regression line, I can use it to estimate a value here, or maybe estimate a value here. Technically, I'm not supposed to extrapolate from it. So I can't just say, well, I'm just going to expand this to the year 2040 and then assume a population. Technically, I can. People still do, but we're not really supposed to, because mathematically speaking, a linear regression equation, or the validity of a linear regression equation, is only valid for the observed data. It's still a method that's used. We just wanted to throw it out there that it's not necessarily valid. So just because a model could be valid for your data here, doesn't mean it's going to be valid for your data afterwards. So whether or not you want to use it to extrapolate really depends on how well you know your model, right? And how well you can assume for the patterns to be repeated in the future. So keep that in mind. This regression method, as interesting, as nice as it is, it's not super convenient. So there are other mathematical methods that allow us to kind of just punch in 2 or 3 numbers in a calculator and estimate, population growth. I'm going to start with what's called the arithmetic method. Arithmetic is the adjective, arithmetic is the noun, but they're spelled the same way, even though they're pronounced differently. So the arithmetic method considers that the growth of a population is going to be linear. Now, I know this should already be, sounding some flags. Wait a minute, growth of population linear, that's not really correct, but it is a method that is sometimes used. And if it assumes that the growth is linear, that means that the change in population with respect to time should be a constant. I am going to call this constant Ka. K sub A. A just stands for arithmetic method. I can integrate this equation, solve for the population, and I get that the population can be estimated as some initial population value, some known population value, plus the growth rate times time. I can say this is the population at time equals t. Okay. Very simple equation. You have dp over dt is a constant, and you just integrate that and solve for p. You need some boundary conditions, and the boundary condition will be a known or measured value. Typically, that value is going to be the population right now, or the latest census, the latest available population data. Of course, we need to know what this k-value is, right? And what we do is we typically look at past data recording. So it's past data census. What's the plural of census? Sounds like
That's some kind of jujitsu.
that's sensei, and that's sensei, and that's Japanese. I'm trying to determine if I'm willing to spend the entire class trying to figure out what the plural of census is. We should move on. Anyway, you need to find, or in order to find your k-value, your coefficient of growth, your constant growth coefficient, what you can do is find population data for one census and for another census, and then you can find the k-value because you're assuming that your growth is linear, and if you assume that your growth is linear, then your growth rate should be equal to the population at your second census minus the population at your first census divided over the difference in time between the first census and the second census. I'm trying to avoid saying the plural of census there. Yep.
It's censuses.
Censuses.
Yep.
Thank you.
Yes.
Thank you. So as long as you have data from various censuses, then you can find what this growth coefficient is, and then you can use it to estimate your population growth. You can see some faces are like, is that really how population works? Not quite. Let's do an example first, and then let's discuss. Okay, so just quick example. Let's say that I'm looking to estimate the growth of the population in a city, and let's say that in 1995, the population was about 100,000, and let's say that in 2010, the population was 110,000. So this is the year, and this is the population. Assuming an arithmetic growth, assuming that the growth is linear, I want to know what is the estimated population in the year 2020. So we want to assume that the growth rate is linear, and using that assumption, we would like to know what is the estimated population in the year 2020. Well, if we assume that this is linear, then we need two points from different censuses, and we can use those 2 points from different censuses in order to determine our growth rate. So I would actually start right there. Let's first find our growth rate. So plugging in your data into this equation, what is our growth rate? You have calculators, right? So use them. 66.7. 66.7? Is that correct? 666.7. Okay, there we go. So let's round up to 667, okay? Good. So we have our growth rate, right, which was 110,000 minus 100,000 divided by 2010 minus 1995, right? So 10,000 divided by 15. Okay. We get 667 is our growth rate. That means that the population at the year 2020 should be equal to some initial value plus the growth rate times the time to that value. So it doesn't matter which one you use as your initial value, your answer should still be the same. So let's just do both. Let me start with my initial value being my 1995 value. So at 1995, my population was 100,000. We add to that the growth rate of 667 times the time. So how much time has passed between 1995 and 2020? 25 years. So put that in, how much does that give us? Okay, 116,666.6 persons. What is 0.6 of a person?
It's over half of a person.
All right. I'm gonna stop this conversation before it becomes uncomfortable. So, okay, we get this value. Let's say we want to use 2010 as our starting point. In that case, the population at 2010 is 110,000 plus our growth rate, which is 667. times however many years passed between 2010 and 2020, that's 10 years. Plug this into your calculator, you should get the same value, 116,666 and 6/10 of a person, right? So this is a simple example. I think if I give you a quiz, this could be something I could give you. I could give you 2 points from 2 different censuses, and I can say, estimate the population at this year assuming arithmetic growth. If I say arithmetic growth, you know it's linear. You plug those in, you get me those values. Now let's actually discuss what are the limitations of this method.
Theoretically, you could have infinite growth.
That's one thing. There's no bounds to how much growth you have. Essentially, this model assumes that as time goes on towards infinity, population tends towards infinity. We know that that's not going to be the case.
You only look at 2 points, so we don't know exactly how the population grew between those 10 or 15 years, 25 years. So it might have been like a really big increase and then really slow, so you can really predict the future that way properly.
Exactly, right? You're looking at 2 extremes. You're not actually seeing the nuances between those 2 points, right? Which means that we are actually averaging the growth. And averaging the growth isn't actually very, very useful when it comes to estimating population growth. That's correct. Anything else?
Population builds upon itself, so if your population grows in 1 year, it's going to grow more in the next year.
Exactly.
So it's exponential.
Exactly, right? Population growth is not linear. There are cases where population growth may tend towards linear or maybe even be less, but those typically involve genocide or other things. So in normal natural cases, population growth will not be linear, it'll be exponential. Good. So we have a couple limitations. I like what you said, Nash. I like what you said, Josh, that, first of all, it's not going to be linear, but also it's not going to tend towards infinity. Right? Population cannot tend towards infinity. There's always like a maximum population, and we cannot really go past that, right? Of course, it depends on our location as well, right? We'll talk a little bit about that in a second. For now, let's look at a second method. This one's called the geometric growth. Try to keep in mind the assumptions behind each of these methods, because a potential quiz question I could ask is, by giving you different sets of data from different censuses, I can ask you something like, which method do you think matches this data the best? And perhaps you won't have time to plug in your equation every single method. Perhaps it's more a matter of looking at how the data trends and then seeing, wait a minute, we can make these assumptions, but we cannot make these assumptions. And then you decide which method works best. So keep in mind the assumptions that we're making. Arithmetic growth, we're assuming that the growth is linear and constant. Okay? So keep that in mind. Let's look at something called geometric growth. Geometric growth assumes that the population increases at a constant percentage. So arithmetic growth assumes that the population increases at a constant rate. Geometric growth assumes that the population increases at a constant percentage, which means if your population doubled in 1 year, geometric growth says that it's going to double again in another year. So the rate at which population grows is the same. We can write that mathematically by taking the derivative of population with respect to time to be equal to some constant called Kp, and then multiplied by the population at that time. So all this is telling me is that the change in population is going to be equal to some constant times the population. In other words, some percentage of that population. For example, if my constant is 1, that means that my population is increasing by 100% at every time step. If my constant is 0.5, that means that my population is decreasing, it's being cut in half, right, at every time step. Of course, there are limitations, and we'll talk about these in a second, but let me first integrate. We integrate this and solve. We're going to get that the natural logarithm of the population at time t is going to be equal to the natural logarithm of some initial population plus my constant times time. We can solve this even further. We can solve for the population at time t, and we'll get the population at time t is equal to some initial population times e to the power of my constant times time. I think this looks a little bit more like the type of growth that Nash was talking about. Is that correct, Nash? Okay, it looks a little bit similar to what Nash was saying. We can solve for this constant. This is actually a percentage rate constant. We can solve by, again, taking data from two different censuses. And we can find that this constant will simply be equal to the difference in logarithms divided by the difference in time between those two censuses. Remember, log b minus log a is the same as log b over a, right? So you can also use that to, I don't know, speed up your calculations or something. Pretty simple method, geometric growth. A little bit more complex than arithmetic growth, but it's still relatively simple in that all we have to do is find out what the growth rate constant is, and then plug it into an equation and find the estimated population. Let's solve the previous example using geometric growth. So in the previous example, what were the numbers? I think for time we had 1995 and 2010. And as far as population went, we had 100,000 and 110,000. So let's now estimate the population at time 2020 using geometric growth. So how do we start? I did the first one, I'll let you do the second one. How do we start? Okay, let's find KP. Let's find that growth rate constant. Let's see. We need data from two censuses. We have that data here. All we need is to take the logarithm or the difference in logarithm between the two populations. So we have the logarithm, natural logarithm of 110k minus the natural logarithm of 100k divided by my 15 years. That gives me a constant of how much?
0.0064.
Okay. Can somebody confirm that?
Yes.
Yeah, okay, good. And now we find the population. We have the equation right here. Population at the year 2020 should be equal to some initial population. Let me just start with the latest one, just makes it easier for me. Some initial population, which is 110k, times e to the power of 0.0064 times time, and between 2010 and 2020, we have 10 years. What's my population there?
117,270.
117,270. Can somebody confirm that value?
Yep.
Okay. In the previous example, we had estimated 116,666 and 6/10 of a person. And here we are estimating 117,270. Which do you think is more accurate? We don't know. This one? Okay. If you're designing, which value would you design for? Okay. What's your name again?
Cassidy,
Cassidy. Why is this one more accurate, in your opinion?
because it gives you more room for error, like more room for the maximum.
Okay, gives you a lot more room. That's good. It's always good to be conservative when it comes to design and politics. But anyway, let's see if we can figure out maybe more conceptually, okay, why this method is better. I like that we're thinking of the math part and the design part, but conceptually speaking, why do you think this method is better?
But doesn't assume linear growth.
It doesn't assume linear growth. But do you think this type of growth is correct?
No. But I think you're looking for a better way. I think it's a better way because you're not making a terrible assumption in linear growth.
Okay.
Because linear growth assumes that two people have 280, and it's just false.
Good. I like that. Good. I like this set. Do you think there's better ways? There's another limitation here. Even though it may seem like it may be a better method than the arithmetic method, there is a limitation, right? You see what that limitation is, and it's a limitation that's shared with the arithmetic growth.
Exponential still.
Yeah, it's still exponential. It still has the possibility of growing towards infinity, and we know that that's actually not realistic. Okay. Just think of it like there has to be a maximum number of people that can live on this planet, right? If you fill up every single square feet of atmosphere and air with a person, eventually we're going to get full. Right? So there's definitely a theoretical maximum. We've got to find out what the maximum is. Now here's the thing. we never, in water research at least, we never actually look for populations of entire planets, but we do think of populations of regions such as cities. And city populations, they can have a theoretical maximum. Sure, we can expand that maximum by adding more stories, building more vertically, but there's still always going to be some maximum. And that maximum, there's a lot of statistical studies and analyses done to determine what the maximum is. But at least from our side, the water resources side, it's not really up to us to determine what the maximum is. It's up to us to determine how soon or how soon we're going to reach it, so we can design for it. Okay. So because we still have the problem of tending towards infinity, let's look at a method that doesn't give us that problem. Let's look at a method called declining growth rate. Declining growth assumes that there is a saturation population, some maximum where the region cannot have a higher population. And as your population approaches that value, your rate of growth is going to decrease. In other words, you have a maximum, and as you reach that maximum, your rate is going to decrease. So you're still going to have increase in population, but the rate at which you increase is going to be smaller and smaller until at time equals infinity, you reach that value. Technically, you never reach that value. Technically, you can get as close as you can to it, but never actually reach it. The derivative then of population with respect to time is going to be equal to some constant called KD times the difference between the saturation population and the population at that time. So think of it this way. When the population equals the saturation population, what's the derivative going to be? Zero, right? Which means that there is no more growth, right? And of course, the further away the population is from the saturation population, the bigger this value will be, which means that the closer it is to the saturation population, the smaller this value will be. So your growth rate is going to be really, really big at first, and then it's going to start decreasing and decreasing and decreasing until at some infinite time we reach the saturation population. We can integrate this equation and solve for my population. Integrating this equation, I get that my population at time t is going to be equal to the saturation population minus the difference in saturation population and some initial population value multiplied by e to the power of negative my population constant times time. This is declining growth rate. Let's solve the same problem. Okay. Oh, by the way, I guess I should tell you how to find this k value, which we can find it by solving this equation from two different points in the census. This k value is going to end up being -1 over the difference in time multiplied by the natural logarithm of the difference between the saturation population and the population at the first or the second census value over the difference between the saturation population and the population at the first census value, right? So let's solve the previous example, but let's assume that the saturation population is going to be 200,000 for the city. So if you don't recall, I think at 1995 we had 100,000, and at 2010 we had 110,000. I would like to know what is the population at the year 2020, assuming that the saturation population for the city is 200,000. Whenever we want to estimate population, let's start first by determining what our constant is. Okay, that constant is going to be -1 over difference in time. So from 1995 to 2010, how many years? 15. Good. Multiplied by the natural logarithm of the saturation population minus the population of the second census divided by the saturation population minus the population of the first census. .007. Is that it? 0.007? Can somebody confirm that value? Yes. Yeah. Okay. So we get a constant of 0.007. We can now use this equation, the declining growth equation, to find the estimated population at the year 2020. Our saturation population minus the difference between our saturation population and some initial population. I'm going to use 2010 as the initial one. Multiplied by e to the negative 0.007, that's our constant, times the time. That gives me a population in the year 2020 of how much?
Is it supposed to be 15 or 20?
Which one?
Calculated
15, because we're going from 1995 to 2010. Right, so this KD has to do with the values that we already have. And we're going to use it to get 2020. But right now we don't care about 2020 when we get the KD. 116,084. Can somebody confirm that?
I agree.
Agree? Okay. It's actually a little smaller than 117,000, so a little bit less conservative. Which method do you think is more accurate? I'm not saying which one would you use. Which one is more accurate? In your opinion.
I'll let you know that the saturated value is actually accurate, I'd say this one, but
Okay.
determining whether the saturated value is accurate or not is probably the whole problem with this method.
Good. Yannick brings up a good point, right? The validity of this method really depends on the validity of that saturation population value. Assuming that saturation population value is correct, then Yannick would say this method would be more accurate. As a designer, which method would you use?
The geometric,
Why?
because it's more conservative.
You're also likely to have your population, the saturated population, change too. Like
How?
over time, like in 50 years, you may have better technology to provide food or resources or whatever, housing
More
for the
construction.
people that are there.
So cities grow, and they don't just grow because people move into them. They also grow in terms of infrastructure, right? The saturation population of Atlanta 50 years ago is very, very different from the saturation population of Atlanta now. It doesn't change that much, but it does change, right? Our capabilities to house people, our capabilities to have infrastructure for people to live in, change. Also, in the case of Atlanta, the whole issue that Atlanta is more of a commuting city also affects the saturated population, because population is not just who's living here, right? We don't design just for people who live here, we design for people who will be here in terms of work. So, yeah.
I was gonna ask if you knew, how old our water system is in Atlanta? Did you include?
I don't know, because when I say Atlanta, I don't say ours. I don't live there and I don't care for it. So, but I don't even know how old the water system is where I live. Actually, where I live, the water system is pretty new, because there was a lot of redevelopment going on. So I really don't know. I know that it's old. I do know that much, that it is old and that it is unsuitable. So there's a lot of work going on. For water resource engineers, there is a lot of work going on in Atlanta in terms of stormwater management, water distribution or supply, and wastewater treatment because of how old their system is. Like you're gonna tell me it's 145 or something. Wow, so quickly. Yeah. Any questions so far? This is not a population density class, so obviously this won't be the focus of the semester. I just want you to give you some general tools so you can come up with numbers on the fly whenever we are designing. Yeah.
So the regression method was only one for like the 1 to 10 years, and the other three were for like 10 to 15.
Right now, everything else is 1 to 10 years. Yeah. So everything we're doing right now is short-term growth. I think for long-term growth, we're going to have to do a little bit more work. But right now, everything we're looking at is short-term growth, which is why we're using this for no more than 10 years, estimated to 2020, and not going beyond that. Okay. And this is a really good point that Yannick makes. This is short-term growth, right? So obviously, we can try to assume linear growth, but not beyond 10 years. We can try to assume geometric growth, but not beyond 10 years. And even with the saturation growth, we can assume saturation growth for more than 10 years, but the equation would be arranged a little bit differently. So this is all still short-term growth. It's very interesting, I would say, because for example, I'm designing two bridges. I think I've talked about this, but I'm doing two bridges in Bucks County. And I started working on these earlier this year, maybe at the beginning of the year, and I pretty much already gone through the hydraulics design I would say it's very done, and coordination with GDOT has happened. It's all going very well, very smoothly. But I looked at the bigger schedule, right, because I'm only the hydraulics engineer, there's structural engineers, there's policy, there's environmental, there's all these different things going on, transportation, geotech. And according to the schedule right now, we are on schedule, but according to the schedule, the bridges are actually scheduled to be built around 2025. That's pretty interesting because when we are planning to build this thing, is also going to affect the flows that are coming, right? So with hydrology, flows change every year as well, rainfall patterns change. So I thought, in 2020, so right now, I wasn't told anything about the schedule. They just told me design a bridge, use these values, use these flows. But I'm pretty sure that when it's time to build a bridge, they're gonna have to call me again and be like, hey, we need to change some of these values. So it's terrible. More money for me, but it is terrible. So as engineers, these are things you need to keep in mind, right? You need to keep in mind how patterns change, everything changes. You don't want to design something for today. You always want to design something for 5 years from now, 10 years from now, 20 years from now, whatever the life of the product is. Corrugated metal pipes, which a lot of the old pipes are corrugated metal, they usually last around 25 years. They were supposed to last around 50 years, but it turns out that after 25 years, they start to erode. And right now, a lot of counties, such as Gwinnett County, Cobb County, Fulton County, are requiring that new constructions use reinforced concrete pipes. What's the problem? Reinforced concrete pipes, yes, they last a lot longer. They're a lot more expensive, significantly more expensive. So it gets to a point where even though the county requires it, the city then says, just use corrugated metal. And you say, okay, see you again in 25 years, right? So it's pretty interesting. The dynamics are really interesting, especially with the way things are growing right now. Like before, it was okay to build something that you knew was going to fail 50 years from now, because 50 years from now you would have been retired, it wouldn't have been your problem. But right now, at the rate populations are growing, structures are starting to fail even before their deadline, basically. So all this you want to keep in mind, especially as young engineers. You're going to work, you're going to design stuff. That stuff that you design is going to get built. And a lot of times, by the time it gets built, you'll be a PE, you'll be a project manager, whatever. You want to make sure that you're proud of what you did. Right? You don't want to be like, yeah, I'm a PE, and this bridge that I made when I was an entry-level engineer just got built, and I look at it and I'm not proud of it. You want to be proud of it. So you always want to make sure, plan towards the future. Let's do a more water-related example. We're still going to do population growth, but all these examples are very bland. They're just numbers. I want to relate this to water supply so that we can at least get some hydrology in this method. Let's say that we are designing for a region, a city, municipality, town, whatever, a region with a population of 200,000 people. I'm just using subscript 1 just for simplicity. My population is 200,000 people. I'm expecting, after doing my analysis, I'm expecting that my population is going to increase geometrically to 200, and let me just call this actually population 0. I'm expecting that it's going to increase geometrically to 220,000 within the next 15 years. Okay, so population right now is 200,000. I expect that in 15 years it's going to increase geometrically to 220,000. There's a bit of carefulness we need to have, right? We need to take care here because right now we're using a short-term method and we're going a little bit above our short-term limitations. But let's just roll with it just for this example. Your region has a treatment plant. And that treatment plant has a capacity of 51 million gallons per day. This is a flow rate because it's volume divided by time. And the input into that treatment plant right now is going to be 165 gallons per day per person. So we typically write this as gallons per capita per day. So gallons per day per person. Okay, my question would be, for how many years would this plant be adequate, assuming that geometric growth? So assuming that geometric growth can last as long as it needs to last. So how can we solve this? I want to know for how many years, or how many years can this plant actually serve this region before I need to upgrade it?
Could you do 51 million divided by 165? Define the amount of population that it can handle,
I like that. I like the way you think. So you're saying 51 million?
divided by the 165.
All right. So 51 million is 10 to the power of 6, right?
Yeah.
Okay. So 51 times 10 to the power of 6. And this is million gallons. So gallons per day. A million gallons per day. You divide that by 165, and this is gallons per day per person. So if everything cancels out correctly, your answer should be in units of persons. Good. What's your name again?
Jaden?
Jaden? Awesome. Oh, you were also in my class. Were you an online student?
I was both.
Both? Okay. So, Jaden, you're the one that doesn't have the laptop. I thought you were two people. There's actually just one student that doesn't have it. And join a team that has a good laptop. All right. I like the way Jaden thinks. Look at your units. You can see that you can actually cancel everything out and end up with persons. So how many persons can this plant support? Okay. Good thing, it seems that the plant is going to work 15 years from now. So how many years, more or less? Let's see, we assume geometric growth. So if we want to know, if we know what geometric growth is, how can we figure out the number of years, I would say?
Or if you want to find your KP value,
We can find our KP value. For geometric growth, I think I have it here in my other notes. KP was the natural logarithm of the population at the second census minus log population of the first census divided by the difference in time between the two. Natural log of 220,000 minus natural log of 200,000 divided by a difference in time of 15 years. Brenda, you good?
Yep.
Okay. I just need KP right now, by the way. I don't need you to give me the final answer. Okay, 0.0061 what?
4.
Okay, we write down our geometric equation formula. had that the population growth is going to be equal to some initial population times e to the power of my constant times t. But here, my unknown is not really the population, right? I know the population I'm trying to get to. I'm trying to get to 309,090 persons. So my unknown instead is time. So in this case, we are going to have to solve for time. How do we solve for time? Let's see, we have pt, I'll just do it step by step. Pt over p naught equals e to the power of kp times t. Should I take the natural logarithm then? Okay, so I take the natural logarithm of both sides, so I get natural logarithm of pt over p naught equals kp times time. You can see here that time is going to equal the natural logarithm of pt minus the natural logarithm of p naught divided by kp. If you realize, this is actually very, very similar. I mean, not very similar, it is. So this is the same as where we get the kp equation. So the fact that kp is constant kind of helps us by just solving, right, for it. So in this case, my target population is 309,090. My initial population, well, depends on when you want to start looking at the time. Let's say I want to start from 15 years on. Let's start from 0. My initial population is going to be 200,000. And that is divided by my kp, which is a constant, 0.00634. This will give me the amount of time starting from 0. So it'll give me, the number of years, the total number of years this plant should last. .02 years.
I got 68.13, but I think it's just rounding.
Okay. Yeah. Good. So, the whole point of this exercise is to say, well, my plant is okay. It's definitely going to meet the target population in 15 years. And if the growth is still the same, it will function for at least another 68.1 years. Notice a couple of things. This is only on the basis of plant capacity. I'm not talking about structural aspects of the plant. I'm not talking about maintenance and operations. I'm only talking about capacity. Okay? There are limitations. Everything we're going to do here, there's no hard science in hydrology, or well, there's no analytical, that's not really correct. There's no nice rounded numbers in hydrology. Everything has to do with a lot of assumptions, a lot of statistical analysis. So in this case, what limitations do you think our procedure has?
Wasn't our second population estimated using a geometric function?
Mhm.
I mean, that's already that's an unknown. Really, we don't know the population of that. It could not be 220,000.
From the very beginning, right? From the very beginning, assuming that there's going to be a geometric growth is a limitation. That is an assumption that we're making, and we're not sure if that assumption will actually be correct. That is the projected increase, and of course, we're going to let other professionals deal with that, but we need to keep in mind ourselves that that is an assumption. There's one limitation, especially in this case, that it's specific, I would say, to the water supply or water treatment thing. So any other ideas of what limitations we may have? And that limitation is kind of there in the given data as well.
The flow?
What happened with the flow?
Oh, you're assuming that everyone's gonna be using 165 gallons per day.
Yep. Now I'm gonna make a comment towards that. So obviously we don't assume that everybody uses 165, but that is kind of like an average value. But there is a limitation with that average value, right? So what are we assuming? So we have 165 gallons per capita per day. And then 68 years from now, we are assuming 165 gallons per capita per day. You think that the average consumption is constant throughout 60 years?
No.
Right? So water consumption changes as well. So this value actually is only a value for right now. And it can change. It can change as easily as in a couple of years, 2 years, 3 years, and definitely will change within 60 years. You know, think of how much water we used before, how much water we use now. Like, even within your lifetime, you can think of how much water you used before and how much water you use now. Okay? Now, of course, there are movements, I would say, in the areas of like environmental science and environmental engineering. There are definitely movements to reduce our water use. So you have all these nice toilets that are designed to use a fraction of the water or something. So there are those issues, but in general, and just based on the current water usage numbers, the usage is always going to increase. So we can kind of reduce the rate at which it increases, but usage will always increase. So we are designing water engineers. It's not just about knowing how much your population will grow in certain years. You also need to think of how your population's water usage will grow in certain years. There's actually a lot more to think of, but at least those two things you want to keep in mind. Population number, your population usage as well. Water usage will change. It's going to vary. Okay. Would you, as a water resource engineer, use the results from this exercise in your design? Why not?
You assumed, you said we were assuming 15 years, but the geometrics was only supposed to go for 10 years.
Okay.
So you're kind of, I guess, you're kind of stretching how much you think your system is going to be able to hold.
Okay. We're using a short-term method. We're expanding it for a long-term. And our conclusion is even more long-term, right? 68 years is a lot more. So what can you do? So as an engineer, as a water engineer, let's say you get hired to study or to assess the quality of this plant, and let's say this is just one part of your work. This is just one small part of your work. When you're studying the quality of this plant, you're studying the capacity. Let's say your client wants to know, or wants you to give him a conclusion on the adequateness of this plant. Will you say, I can conclude that this plant will be adequate for the next 68.1 years? Okay. Would you say, I can conclude that based on the projections, on the current projections for the next 15 years, the water plant will be adequate for the next 15 years? I think that's something you could say. I would obviously recommend a little bit more to be done. Of course, look at water usage trends and whatever, but because we fall well within a nice range, we could say that. Now, of course, I'm not saying go ahead and say that. There's a lot more to be done, but I want you to keep in mind that there are statements that we can say with some certainty. There are statements that we can certainly not say. Like, I can be sure of what not to say, and I can be more or less sure of what to say. And that's going to be a very important trend in water resources. So never say, I know for certain that this can happen. You can only say, based on the given information, this may happen, or you can say, for sure this will not happen, but not the opposite. Okay. So let's keep that in mind when it comes to water resources and when it comes to drawing conclusions. I'm doing an assessment of a wastewater treatment plant in the Virgin Islands. I mentioned that earlier in St. Thomas. And one of the things we need to provide with our assessment is whether or not this treatment plant is adequate for the construction of a new apartment building. Now here's the thing, we don't really have projection estimates for the apartment building. So we don't know if they want to make it, we don't know how many people the apartment building wants to serve. So we need to frame our conclusions in such a way that we can take into account any possible scenario. And so that the client knows what the limitations of our study are. Okay? Let's keep all that in mind. I wish I would have done this project a year ago so that I could incorporate it into the workshop. But it's still an ongoing project, and I don't want to incorporate ongoing projects because there's like free labor thing or whatever. I know people that have done that, that they just bring their own projects and like, students do it for free, and then I get paid. I don't want to end up falling in that area, so I'm only incorporating very, very, very old projects that I've already completed and already gotten paid for. I cannot get paid again. But if I teach this class next year, I'll definitely bring in the wastewater treatment plant study in St. Thomas. It's a really, really nice study. And maybe I can talk to you about it or bring one of my interns or employees to talk to you about this project. It's a very good project. We have 15 minutes left, and let's use the remaining time to look at some of the long-term growth models. Long-term growth models are not as mathy, not as simple as these short-term models. They require a little bit more analysis. They require a little bit more observations. But if done correctly, they could be valid models for a design. I mentioned that infrastructure, typically you want it to last about 50 years. It's not going to last that long. We typically want it to last about 50 years, maybe not longer. So let's try to make sure that we keep these long-term models or use these long-term models for about the next 50 years. Okay? One long-term model is the comparative growth model. Comparative growth has obviously, like any other model, its strengths and weaknesses. The idea behind comparative growth is to look at larger populations in your vicinity and then assume, right, that your population is going to follow the same trends as the populations that are near you. There's obviously a lot of assumptions done there. There's a lot done there that we're not entirely sure. But the base idea is, if you're in a region that's surrounded by similar regions, and this is a little bit hard when it comes to cities unless there's cities nearby. So for example, you can think of North Carolina, Raleigh, Durham, 2 cities. You can actually use a comparative rate to estimate the growth between the 2 cities. Because we have Raleigh, we have Durham, and we have Chapel Hill and Wake Forest, which are more or less similar size to each other and also in that same area. So the idea would be to look at nearby regions that have similar properties, see how they have grown, and they have to be bigger than yours as well. See how they have grown, and then applying that growth rate to your population, or that growth percentage to your population. This is actually a method that is used a lot when you have a growing smaller city within a larger city that's already been developed. So like I said, we have Wake Forest and Chapel Hill, and we have Raleigh and Durham. Raleigh and Durham are really big. Wake Forest and Chapel Hill are growing, right? And we can use comparative methods to estimate their population growth. Same thing can be done even when it comes to Atlanta and the neighboring cities such as Sandy Springs and Dunwoody, right? Cities that are relatively new, right? Relatively new, and that still tend to follow a growth rate. People, you can actually see that, right? Especially with the whole migration of companies outside the perimeter. But you can see that the growth of Sandy Springs is almost mimicking the growth of Atlanta 20 years ago. Right? Just like Atlanta just like exploded with a bunch of buildings, Sandy Springs is doing the same thing. My wife, before we got married, my wife used to live in Sandy Springs, and she lived in an apartment, and there was nothing. It was just like her apartment, and we had a nice restaurants and whatever. But now when we drive by that area, it's Hammond Drive, by the way, it's just buildings, high rises everywhere that they did not exist just 5 years ago. So Sandy Springs is exploding at the same rate as Atlanta was several years ago. So comparative growth works. You need to be very, very good at this idea of urban planning and population in order to use it correctly. I can't apply it all the time. So I can't go to 2 cities and be like, oh, this city is nearby this city, I can use comparative growth, because it really depends. For example, I can't go to Long Island and then try to apply the same growth of Manhattan into Long Island. Okay? So there's always limitations. I can't go to Wheaton and try to apply the same growth as Chicago. Okay? There's always limitations to our studies. Okay? In this class, I would not use comparative growth that much, just because it does require a lot of extra work outside of water resources engineering, and of course this is a water resources class. But it is important for you to know. It is one of those methods that is available for us to use. What limitations do you think a method such as this one would have, besides what I've already said?
We're assuming things that you really can't assume, because there might have, some things might have happened in the bigger city or in the bigger region, and you can't expect those exact same things that also happen in your region.
Okay,
so they have similar properties.
So comparative growth pretty much requires a thorough knowledge of the history of that growth, right? Of everything that's going on in the background, everything that influences that growth. We may have had an industrial boom at one time. Perhaps we don't have that industrial boom right now, so we can't really assume that the growth that came with that industrial boom is going to be now. We have tech booms right now, right? But that may not be the case 10 years from now, 20 years from now as well. So it's very, very important for you to have a good idea of the history behind whatever it is you're studying, all the nuances, everything that's happening in the background. Thankfully, I don't really deal with this, so thankfully that's not really part of the water resources work. But if you've taken my fluids class, you know that I don't like for you to just take a number from someone, take it for granted, and then just use it, right? You want to know exactly what it is you're doing and where that's coming from, okay? So that you can know what the limitations are. Because if you receive a population growth estimate, yeah, you can assume that the estimate is correct, but in the end, whose signature and seal is going to be in the design? Yours, right? So in the end, you are liable. So there's always ways to word your report and be like, based on this information, whatever, but why not just play it safe and know what it is you're studying? One of the things I always try to teach my interns is that even if I give them a number, don't accept it unless they know where I got it from. Because even for me, I sometimes use numbers that maybe they were valid in Puerto Rico, such as average rainfall numbers. In Puerto Rico, for example, Puerto Rico rainfall, it's not like specific for every single watershed, but in general, rainfall is about 6 cubic feet per second per acre of watershed. And you can use that to estimate some large watersheds and kind of give a ballpark estimate of how much a project is going to cost to your client before you do the final analysis. And it usually gives close values, not exact, but close values. Puerto Rico has a lot of mountains, it has a lot of rainfall. Come here to Georgia, it's actually not that's not the case. Average rainfall is about 2 to 3 cubic feet per second per acre of watershed on the rural areas. Okay? So when I'm working with my interns, sometimes I just throw out the 6 CFS number. Oh, 6 cubic feet per second. That's actually not really valid for Georgia. So I want them to be like, where did you get this number from? Right? And I'm like, oh, wait a minute. No, I got this number from my work in Puerto Rico, so it won't be valid here. So never, never, never take anything that anyone gives you for granted. Let's look at another type of growth. This is logistic curve growth. And this is a little bit more like the regression method that we talked about, which considers assuming that everything grows at a power rate. So that you can plot everything as a straight line in a logarithmic curve. The equation for logistic growth is not really it's not an equation that can develop mathematically from a derivative. It's actually an equation that was developed from a lot of statistical analysis done by people that know about this more than me. And the equation is as follows. We take the population at a time t to be equal to the saturation population divided by 1 plus a times e to the power b times t, where a and b are constants. And those constants can be determined by looking at not 2 but 3 census records. When we're looking at geometric growth, all we need is 2 former census records, because we assume that either the growth rate is constant or that the rate or that the percentage growth is constant. In logistic curve, we're assuming a power relationship. And for any power relationship, we need more than 2 points, right, to understand what that graph will look like. So we need 3 points. If we can obtain 3 different points, let's say that we have time 0 and population 0 for that time 1, population 1 for that time, and time 2, population 2. So if we can get a census and obtain the 3 different points for that census at different years, then we can estimate things like the saturation population, which can be estimated as a function of these 3 points, because saturation population is the asymptote, right? We know that our curve will never reach it, but it will always be tending towards it. Saturation population, I'm just going to write down the equation here, is simply 2 times the product of all my populations. I'm not even going to say, I'm just going to write it. Saturation population, and then my constants A and B can be obtained as follows. This model, I mean, you may recognize these equations a little bit, or the form of these equations, but this model is essentially fitting a curve into a power curve, or fitting an equation into a power curve. That's all it is. So we need 3 points, and we have those 3 points, we can fit an equation and find the asymptote, and we can find the 2 coefficients. In this case, we have this variable n, and n is just the distance or the time between P naught and P1. So time between P naught and P1. This is the logistic curve method. If you have your textbooks already, you can look at example 1.5. I think that gives us a nice little usage of this method, but I don't think we have to go over in class. It's just more of the same thing of plugging numbers into an equation. But look at your textbooks if you want, and that way you can practice a little bit with it. Quick question, did anybody actually opt to get the Day 1 Access and get that book? It's a supplementary book, so not really necessary, but did anyone actually get it? Okay, so if you did, let me know over email so that I can go over the book and maybe look at which sections correspond to what we're covering. That way you'll be able to use it a little bit better instead of just trying to find everything yourself, okay?
On B is that of the top one, so it's P stat minus, is that P naught or P1?
P naught.
Okay.
Well, P naught, P naught. P naught, P naught, and then this is P1, P1. So logistic curve growth, you can do your example from the book, example 1.5. We have 2 more minutes. I do want to go over, at least discuss or explain the other methods. We have a method called growth by ratio, and all this is in your book, by the way. And growth by ratio, all it means is that we assume that if your region is part of a larger region, let's say your city, Atlanta, is part of Georgia, we assume that the growth of your smaller region is proportional to the growth of the larger region. Of course, there are limitations. For example, with states that are typically rural but that have large cities, such as Illinois and Georgia, the growth of the city itself is going to be exponentially larger than the growth of the rest of the state. So there are limitations. But if you can find your small region to be part of a larger region that has similar properties, then you can do growth by ratio and just say, if the state is expected to double in size, then my city is expected to double in size as well. Remember, that doesn't really work for rural states with large cities, but it does work for places where the large region is similar to the small region.
Like California?
Yeah, California is one of the states where growth by ratio is used.
Good.
Growth by correlation essentially says that the relationship between the small region and the large region can be obtained through a linear relationship. So it's kind of like a regression method, but instead of using existing data from your region, you actually use existing data from the larger region. And then you scale it down into your region. So it's another regression method that requires 2 regions, a small one and a large one for it to use. And finally, growth by components is essentially applying a continuity equation, a conservation of mass equation, into our population growth. How does population change? Birth, death, migration. So my component method just says that my population will be equal to my initial number plus births minus deaths plus migration, assuming that migration is into the region. It's simply a conservation of mass. It's 1:45. Let's end class here, and I will see you next week.